welcome everyone to the second day of this particular school. So today's first session is mostly about 21 centimeter cosmology and how does 21 centimeter cosmology changes if you change the fundamental basic cosmology model behind it. So first speaker is Professor Kanan from Jadavpur University, and the next speaker is Tapumay Ghosh from BITS Pilani. So Kanan.
Thank you.
So sorry, just to make sure that we started roughly 10-15 minutes late. So this lecture will basically go up to, let's say, 15 minutes extra. So 10-15 and then Professor Ghoshkar will start.
Thank you, Suman. So I have been asked to give a lecture on basics of 21 centimeter cosmology. So I shall start with something that you all are familiar with. So you see, this is this shows the energy level of hydrogen atoms, and you see Lyman series transitions, Brahma series transitions. So today I shall focus mostly on the ground state of neutral hydrogen, that is n equal to 1. But I shall also talk about importance of Lyman alpha photons in certain aspects of 21 centimeter cosmology. So most of the hydrogen in our universe during reionization and before reionization, like cosmic dawn and dark ages, they are in ground state. And the ground state is split into two hyperfine states. One is called triplet state, and the other one is called singlet state. So, so why there are two hyperfine states? So let me explain that. So the ground state, which corresponds to n equal to 1, has 0 orbital angular momentum. So L equal to 0. But electron has a spin, and also proton is a spin half particle. So if I calculate the total angular momentum, which is the sum of electron and proton spin. So F equal to I plus S. F is the total angular momentum, I is the proton spin angular momentum, and S is the electron spin angular momentum. And both are half. So when proton spin and electron spin, they are aligned, that gives me the value of F equal to 1. And when they are anti-aligned, that corresponds to total angular momentum F equal to 0. And if I take projections, this F of the triplet states, it will be +1, 0, and -1. So triplet state has it's a degenerate states with degeneracy value of 3. So it has basically 3 energy levels, but with same energy. So this line was first predicted by this person, Hendrik van der Hulst, 1944, and it was experimentally discovered in 1951 by Purcell and Ian and Purcell, but that is from our own galaxy, not from the cosmological H1. So let's try to understand how this ground state is splitted into two parts. So electron has spin, so it has spin angular momentum, and also proton has spin. So you can think of proton creating magnetic field around it, and electron, since it is a charged particle, it is experiencing that magnetic field. So there is an interaction between proton magnetic field and electron magnetic field, and due to this interaction, so this ground state is splitted. Okay. So if I calculate electron magnetic moment, that is mu e, and you can write that as this, and you see this depends on the spin vector S, where this mu b is Bohr magneton, and the value of Bohr magneton is this for electron. If we calculate magnetic moment for proton, and so you can write proton magnetic moment as this, and since proton is much heavier than electron, so proton magnetic moment is much lesser because of the mass which comes up in the denominator. Now, because of this interaction between magnetic moments of electron and proton, the corresponding potential energy is E equal to minus mu dot B, where mu is the magnetic moment and B is the magnetic field. So now you understand that why there is interaction between proton and electron. That's basically due to the magnetic field created by proton and electron, and the corresponding potential energy is this. Now, if we actually calculate that potential energy, it comes out to be something like this. So there are some constants, but then you also have this S dot I. S is the spin vector of electron, and I is the spin vector of for the proton. So S dot I. Now, if we further elaborate it, so S dot I can be written as this. So this is S dot I is an operator, and you know how to write that operator in terms of F, S, and I. So this is S dot I is this. Now I showed that F can be 1, it can be 0. So for triplet state, F is 1. So for triplet state, S dot I is this. So if I just put F value 1 and S and I both are half, so S dot I for triplet state is 1/4 h cut square. And for singlet state, it is negative because F is 0. So these two terms give you negative values of S dot I, right? So, so now you see that if I take the difference of energy between two hyperfine levels, that is delta HF, that is the difference between energy of triplet state and energy of the singlet state. And that, so if you use the same expression and put all the values of constant, you will get something like this 1422.8 megahertz. But if you do some more precise calculation using QED, it comes out to be 1420. So that's how this 21 centimeter. So this and corresponding wavelength is 21.11 centimeter. So that's how this signal arises. So it's basically splitting of the ground state of hydrogen and transition between triplet state and singlet states, and that gives you this 21 centimeter signal, right? And okay, so now we understand this. So moving forward, why we are interested in the hydrogen atoms? So if we see the energy budget of our universe, you might have seen this picture already. So if you look at the energy budget of the universe, around 70% is dark energy and 25% or so is dark matter, and both are largely unknown to us. The rest 5% is something that we are aware of, that is the baryon. So that constitutes only 4% of the total energy budget of our universe. And out of this 5%, this baryon, 75% in terms of weight, it is in the form of hydrogen. So whatever we know, most of them are actually made of hydrogen, and rest 24% is helium, and rest 1% is higher elements, all the higher elements that we see. So that is the energy budget of our universe. So now you realize that why hydrogen is so important. So it is basically the dominating component of the known matter, that baryonic matter. Now, so this picture you have seen many times, but for completeness, let's go through it again. So we are at the present, at this position, present universe, and if you look back, you see universe became completely neutral during the recombination epoch. So during the recombination epoch, at around redshift 1000, a proton and electron combined and formed neutral hydrogen atoms, right? So after that, universe actually became fully neutral. So after redshift 1000, universe became completely neutral, with 75% of it is in the form of hydrogen and 24% helium. And during this episode, there were no luminous sources like stars, galaxies. And it is believed that around redshift 20 or 25, first sources appeared, and that started to ionize the surrounding neutral medium, right? And during reionization, so the reionization is completed by redshift 6 or so. So you see, you have a lot of neutral hydrogen during dark ages, cosmic dawn, and epoch of reionization. So it is a good tool to study. If you want to study epoch of reionization and cosmic dawn, H1 21 centimeter is a excellent tool, and there are a lot of efforts. You have already heard about that, to actually detect that signal and study the epoch of reionization, the large scale structure of the epoch of reionization. And 21 centimeter signal is in the radio range, so you can observe that light from using a ground-based telescope. You don't need to go to space to observe it, and yeah, and it is all over the space, so you can probe the large scale structures, right? So there are several advantages, and people are actually trying to detect the signal from epoch of reionization. Now, what the actual quantity we can measure regarding the 21 centimeter signal? So look at this picture. So we have this cosmic microwave background radiation coming from redshift 1100, right? And that radiation is passing through the neutral hydrogen cloud, and we are observing it from the present epoch, from ground-based telescope. So now, if you imagine that there is no cloud, cosmic microwave background radiation is just simply passing through an empty space and reaching to us, we will see a spectrum like this. So cosmic microwave background radiation is a perfect black body radiation. So if we see the spectrum as a function of frequency, it will look like this. It's a perfect black body spectrum, right? So we expect to see this kind of spectrum if there is no neutral hydrogen between the last scattering surface and the present epoch. However, we have neutral hydrogen, right? And so it will actually so 21 centimeter signal from the neutral hydrogen cloud will be added to the CMB background, or depending on its spin temperature, it might also absorb some of the 21 centimeter photons from the CMB background. So that's how it will affect the observed 21 centimeter spectrum. So actually, rest of the frequency will not be affected by H1, but it can affect the 21 centimeter radiation of the CMB background. Right? So you might see something like this, or you might see something like this, either emission or absorption, depending on a quantity called spin temperature, right? So you will see some distortion of CMBR background radiation due to the intervening H1 medium, and that is the deviation we are interested in. So we are interested in the deviation created due to the H1. So that is called differential brightness temperature. It's a difference between spin temperature and CMB temperature. If there is no H1, then it will be like CMBR, right? Right. Now, what is spin temperatures? I have already told about spin temperature. What is spin temperature? So spin temperature, so as I explained to you that there are two hyperfine states, triplet state and singlet state, and hydrogen atoms can be in triplet state or it can be in singlet state. And there are several processes by which a hydrogen atom can go from singlet to triplet, right? There are several processes, and they are in equilibrium. So if you take the ratio of N1 and N0, N1 is the number density of hydrogen atom in triplet state, and N0 is the number density of hydrogen atom in singlet state. If you take the ratio and write in terms of Boltzmann equilibrium, so N1 by N0 is equal to G1 by G0 e to the power T star by Ts, right? If you write in that fashion, then this Ts is called a spin temperature, right? So it is defined as this, where T star is this quantity H nu21 by Kb, and that value of T star is 0.068 Kelvin, right? And G1, G0 is the degeneracy parameter. So here it is, in this case, G1 by G0 is 3, because triplet state has 3 degeneracy parameter, and G1 is the degeneracy parameter of singlet state. So, now if we know this ratio, if you know the relative population of singlet state and triplet state, you can easily calculate spin temperature. Or vice versa, if you know the spin temperature, you can actually calculate the ratio of triplet state and singlet state. Now, so for example, if Ts is much higher than the T star, so this factor will be very close to 0. That means N1 by N0 would be just G1 by G0, which is 3. That means 3/4 of the total atom will be in the triplet state, and 1/4 will be in the singlet state. And that is the case in practice. So we have around 75% of ground state atom in the triplet state, and only 25% is in the singlet state, largely. Right. Now, what are the processes by which atom can go from singlet state to triplet state and triplet to singlet states? Because that will determine the spin temperature, right? So the first process that we can think of is the spontaneous emission. So let's say you have a neutral hydrogen atom in triplet state, and if you leave it alone, then there is a chance that it will decay to the singlet state. But the decay rate is given by this quantity, Einstein A coefficient, and that value of that is 2.85 times 10 to the power minus 15 per second. And if we convert in terms of time scale, it is around 10 million years. That means if we just take hydrogen atom in triplet state and leave it alone, it will take around 10 million years to decay to the singlet state on an average, right? So it's a very slow process, but you have plenty of neutral hydrogen out in the space. So that's how you get some finite amount of 21 centimeter radiation, right? So this is the first process. But apart from that, there are several other processes by which this transition can occur. So this is radiative transition. So if you have radiation background around 21 centimeter wavelength, so we have already, because we have CMBR and it has this 21 centimeter photon as well. So if you have if you have hydrogen atom and if it is inside the CMBR background, 21 centimeter frequency, 21 centimeter wavelength photons will excite a singlet state atom to triplet state, or it can also affect the triplet state by stimulated emission. So CMBR photon can also actually it can also help to decay this triplet state atom to singlet state atom. That is called stimulated emission and stimulated absorption. And both process is dependent on the radiation background, the intensity of the radiation background. So if there is no radiation background, then this process will not occur, right? You have also collisions. So there are collisions between hydrogen atoms, hydrogen electrons, and hydrogen photons, right? And due to these collisions, these are thermal collisions. If you have a thermal gas, they collide with each other, right? So that's it. Now, if you have these collisions, atom can go from singlet to triplet and triplet to singlet state. So apart from these two processes, there is another process called Lyman alpha transition. And Lyman alpha transition is something, so let's say you have this Lyman alpha photon in the medium. So what Lyman alpha photon will do, it will excite one ground state atom to the n equal to 2. That means first excited states of hydrogen atom. So it will go to the either of these hyperfine states, but then it will come back to the ground state again. But while coming back, so let's say it starts from singlet state, it go to the state corresponding to n equal to 1, n equal to 2, and then it comes back to triplet state. So it starts from singlet, but it comes back to singlet states. So this is an indirect excitation to the triplet state. And the vice versa can also happen. So one atom can start from triplet state, go to the n equal to 2 state, and come back to the singlet state. So that's how this Lyman alpha photon can also contribute to the triplet to singlet state transitions. Now, if we take the rate equation, if you consider all of the processes together, so n dot is the rate of change of number density of atoms in the ground state, and that is occurring due to these processes. So you have this P01 gamma, that is the excitation rate of atoms due to the radiative transition, radiative excitation. And then this is the excitation rate due to the collision, and this is the excitation rate due to the Lyman alpha transition, right? And this is the de-excitation rates, and that is proportional to the number density N1, that is number density atom in triplet state. So you have excitation rate, you have de-excitation rate, and if you combine these two processes together, you get this rate of change of N0, right? Okay. Now, so now if we consider each processes individually, let's say there is only CMBR radiation and hydrogen atom, nothing else. Now, in that case, so you have your spin temperature will be same as CMBR temperature. So if you have CMBR, it will always interact with the hydrogen atom, and the corresponding spin temperature will be in equilibrium with the CMBR temperature. So in that case, TS will be same as CMBR temperature, and we know the CMBR temperature, right? So this so these two processes, this is the excitation rate and this is the de-excitation rate, right? So this is the excitation rate due to the CMBR excitation, and this is the de-excitation rate. So stimulated emission and stimulated absorption. And if we calculate this ratio P01 gamma by P10 gamma, you get this N1 by N0, and we have already defined this N1 by N0 is 3 e to the power T star by TS, but here TS is T gamma. So basically this ratio becomes equal to this. Here this exponential term actually has been linearized as 1 minus T star by T gamma, because T star by T gamma is a very small quantity. T star is 0.068, but in fact T gamma is much more than that. During epoch of reionization, it is around 30 Kelvin, 40 Kelvin. So this ratio is very small quantity. So that's how we can write e to the power x as 1 plus x and ignore the other higher order terms. So that is what we have followed here in this calculation. And this is true for other two processes also, for collisions and Lyman alpha transitions. So if we calculate the ratio of excitation rate and de-excitation rate for the collision only, so if we consider only collisions, then we can write this as this. And here the spin temperature is exactly equal to the kinetic temperature of the gas, right? So because there is only collisions, and collision will bring the spin temperature equal to the kinetic temperature. So kinetic temperature corresponds to the kinetic motion of atoms, right? So and for Lyman alpha transition, the corresponding temperature is color temperature. But again, Lyman alpha photon is continuously absorbed and emitted by hydrogen atoms. So eventually, this Lyman alpha photon will also be in equilibrium with the kinetic temperature. So this color temperature is essentially same as kinetic temperature, right? So now during equilibrium, so equilibrium means this n dot 0 is n0 dot is 0. That means in equilibrium you have the total number of transition from singlet to triplet is same as transition from triplet to singlet. So they balance each other because it is in equilibrium, right? So things doesn't change. So n0 dot is 0. So that means these two things are exactly opposite to each other. So I write this here, and I use the equations, the relations that I have already discussed. This P01 C by P10 C, all these relations that I have already discussed. If I put all of them together here and do some simplification, I get spin temperature as this. So spin temperature inverse is this. So it depends on CMBR temperature, kinetic temperature of gas, and color temperature. And you also have this XC and X alpha, which are written as this. XC is the ratio of to excitation and de-excitation rate due to the collision and gamma, same as X alpha. So so you can actually derive it. It's not a difficult calculation. It's a very simple calculation. So, but ultimately we can calculate spin temperature if we know CMBR temperature, kinetic temperature, And as I said, color temperature is same as kinetic temperature. So if I know CMB temperature, kinetic temperature, and collisional coefficient and Lyman alpha coefficient, we can calculate spin temperature, right? Because we need to know spin temperature in order to know the relative population, right? So xc can be written as this, where k10 value is given. This comes from atomic physics calculations, and this is written here from this reference. So one can use this relation. And for x alpha depends on the background Lyman alpha photons, right? So this x alpha can be written as this, and it depends on J alpha, which is flux of Lyman alpha photons. And you have heard from Girish yesterday how to calculate J alpha, the Lyman alpha background. So if you calculate, so this comes from galaxy formation theory, right? So how bright your galaxy is, and what amount of Lyman alpha photon it is emitting and escaping from the galactic environment. So all these things go into this J alpha, and you can plug that in here, and you will get X alpha, right? So here is the here are two plots which is showing the temperature as a function of redshift. So if we look at this plot, x-axis is the redshift axis, and this dot line is the CMB temperature. So it falls as 1 plus z, right? However, if we look at the red solid line, it shows the gas temperature, that gas kinetic temperature, and you see initially it is coupled to the CMB temperature, and that is something I did not discuss. This is because of the free electrons available in the intergalactic medium. I think Tirth touched on this little bit. But as gas temperature falls much rapidly compared to the CMB temperature as 1 plus Z square, if there is no external heating, then it will cool faster than the CMB temperature, and the gas temperature will come below the CMB temperature. However, during the reionization, you have these X-ray sources and several other candidates that can heat up the gas temperature again, and it can rise up the gas temperature, gas kinetic temperature like this above the CMB temperature. One more point that if you look at the dashed line, shows the spin temperature, the one that I have already just discussed. So this dashed line, so initially spin temperature and gas temperature and CMB temperature all are same because everything is in equilibrium. However, later you see this spin temperature, that is dashed line, is following the gas temperature. And that's because initially collision coupling is much stronger, and collision coupling depends on the density and temperature, and both of them are very high at higher redshift. So initially collisional coupling is very strong compared to the other Lyman alpha coupling thing. So that's why it is following the gas kinetic temperature. But later gas temperature, you see it is spin temperature is rising and is trying to follow the CMB temperature. And that's because as the universe is expanding, the density and temperature both are decreasing. So collisional coupling becomes inefficient and radiative coupling becomes dominant. So radiation can now determine the spin temperature. So it is just trying to, the spin temperature is trying to catch the CMB temperature because of the radiative coupling. But then again, you have this Lyman alpha photon coming from the fast stars, galaxies, because Lyman alpha photon can only come from galaxies and stars. And that Lyman alpha photons, again, you have this Lyman alpha coupling, and that will again try to bring down the spin temperature, and it will couple with the kinetic temperature. right? So three processes, they are important at different time of the cosmic dawn and dark age phases, right? Yeah, so same plot, but here I do not show the laminar alpha coupling, but only radiative coupling and collisional coupling, right? So far we have discussed spin temperature and how to calculate it, and what are the processes that actually determine spin temperature. Now let us focus on transfer of 21 centimeter signal through the intergalactic medium. If I go back to my this plot, so you have this CMBR, cosmic microwave background radiation, and it is passing through the intergalactic medium, which is mostly made of neutral hydrogen, helium, right? So, right. Now, before I try to solve the radiative transfer equation in this context, let me introduce some basic quantities regarding it. So, first quantity is specific intensity. That's something that Ilian yesterday introduced. The specific intensity is it is basically defined as energy received per unit area, per unit time, per unit solid angle, and per unit frequency. So if some radiation is coming from this side and you have a detector, so you can calculate the amount of radiation received per unit area, per unit time, and per unit solid angle and frequency, and that is your specific intensity. Now, specific intensity can be direction dependent. It depends on the source population, source distribution. But if you want to measure the mean specific intensity, you have to actually take average over all solid angle, all over the sky. And that is called J nu. So the J nu is basically spherically averaged specific intensity. The unique point for this specific intensity is that in free and non-expanding space, specific intensity doesn't change. So specific intensity at different locations will remain same. It will remain throughout its propagation if the space is free and if it is non-expanding. So one can prove that, and you can actually go to this book, as a famous radioactive astrophysics book by Rebecca Lightman, and so you can get much more details of that. Now, if I consider a black body, this is the black body relation for the black body spectrum, and so this black body spectrum can be completely determined by the temperature. So if I know the temperature, I can draw the black body spectrum, right? Because all other quantities are known. H, so nu is given, H, Kb, all C square, all these quantities are given. So for a specific temperature, I can plot the black body spectrum as a function of frequency, right? And in the Rayleigh-Jeans approximation, that means when frequency is much smaller, that means this ratio is much smaller than 1, then one can approximate this e to the power x as 1 plus x, and 1 will cancel out. So this expression can be simplified as this: dt is 2 nu square by c square kBt. So this is a very simple relation, and this brightness basically essentially the same as specific intensity. So if I measure specific intensity of a particular source, I can immediately calculate a temperature, TB, using this relation, right? Using this relation, I can calculate the temperature, and that is called brightness temperature. So if it is a black body, then this brightness temperature is temperature is same as the black body temperature. If it is not a black body, it will give you a temperature that is associated with this spectrum. So we can always associate a source with some temperature. So we can assign an effective temperature given this specific intensity. So if I know specific intensity, I can calculate temperature. So that is called brightness temperature, right? So that, keep that in mind, right? Now, one more thing, that so universe is expanding, right? If it is not expanding, then specific intensity will remain same along its path. But if it is expanding, then specific intensity will not remain same, and you can calculate the specific intensity using this relation. So basically, if you know the specific intensity at the location of origin of the radiation, you can calculate the specific intensity at later time using this relation, right? And temperature of that source, the effective temperature will also go down as 1 by 1 plus z. So if it is expanding, temperature will reduce by this factor 1 plus z. So this is the brightness temperature that will reduce. Right. So with this background, now let us consider this picture. So you have this CMBR background, and it is passing through some neutral hydrogen cloud. Now we want to measure specific intensity at our location, right? We want to measure specific intensity at this location. We know initial specific intensity is I nu 0, that corresponds to the background CMBR, because there is, so from when it enters the H1 cloud, the specific intensity will be same as the CMBR specific intensity. But when it will come out of the cloud, its specific intensity will be something different. So the corresponding equation that actually gives you specific intensity at different location is given by this equation. So d I nu dl is j nu minus alpha nu into I nu. So j nu is called emission coefficient, and it is, so this is emission and this is absorption. This minus alpha nu I nu is the absorption. If there is no emission, no absorption, then I nu will remain constant, right? Because it will be 0 and I nu remain constant. But if you have emission and absorption, it will change, right? So how do you define emission coefficient? It is essentially energy emitted per unit volume, per unit time, per unit solid angle, per unit frequency, right? So this cloud will add up some 20 centimeter radiation to the CMBR background, and that depends on the source properties. And so this is emission coefficient, but it can also absorb radiation from the CMBR background, and that is given by alpha nu I nu, and alpha is the absorption coefficient. It is defined as this. du nu is equal to this. So absorption coefficient is defined as radiation absorbed per unit area, per unit length, per unit time, per unit solid angle and frequency for this given I nu, right? So this is the equation, and so I divide this equation by alpha nu both sides. So this dl alpha nu will become d tau, and this s nu is j nu by alpha nu, and so this equation becomes this, and s nu is the source function, and tau here is the optical depth, because d tau is alpha nu dl, right? Now this source function, if it is CMB background, so source function is corresponds to the H1 cloud, and that will so if I solve it, so if I solve this equation, if I solve this equation, the solution would be this. So I'm not proving it, but it will be like this, and it is given in the Rebecca-Leibman book. So you see this B nu TS term appears here, and that is the brightness due to the H1 cloud. So H1 cloud is adding some 21 centimeter photon. So BTS is the corresponding brightness, and tau is the absorption, alpha nu DL. And so this is the solution. Now, as I said, that specific intensity can be also written in terms of temperature. So this specific intensity equation can be rewritten in terms of temperature. You have to divide by 2 nu square by c square both sides, and you will get this equation, right? So this is the solution. TB, that's the brightest temperature that I will observe at this location from by the observer will be this TB, that is equal to TS minus into 1 minus e to the power minus tau this. Now, if tau is 0, right? If tau is 0, that means if there is no absorption, then this is T gamma, simply T gamma, and this will be 0. So if there is no absorption, TB will be simply T gamma, right? Right. So T gamma. So that means it will remain as the CMBA temperature. So T gamma is the CMBA temperature. But if tau is not 0, if it has some finite value, it will be like this, right? Now, yeah. So this is yeah. So this these are the few relations, and then tau is this, right? Now, now the final part is that. So as I said, we are interested in the difference with respect to the CMBR, right? Because we want to know the impact of the neutral hydrogen, and that's how we can probe the neutral hydrogen. So, so differential brightness temperature is delta TB. So far we have talked about TB, right? So far we have talked about TB. Now we want to know the difference being created by the neutral hydrogen, and we define differential brightness temperature as TB minus T gamma, because we want to know the change that is occurred due to the intervening neutral hydrogen medium. So TB minus T gamma. If it is TB is same as T gamma, then delta TB will be 0. There will be no impact of interelectric medium. Now this T gamma, now if I put this T, so TB is this, and we have also divided by a factor 1 plus Z. That's because universe is expanding, so radiation temperature will scale as 1 plus Z, like all other radiation, CMBR radiation and any other radiation. So this is the temperature that we can observe, and if I, so TB is this. Now if I assume tau is much less than 1, one can show that this equation becomes this. Delta TB is T spin minus T gamma multiplied by tau 1 plus Z, right? So you can actually so if tau is much less than 1, then this becomes TS 1 minus 1 plus tau plus 1 minus tau. Now this cancels out. So what is left is tau TS minus T gamma plus T gamma, right? So basically TB minus T gamma, which is the differential brightness temperature, is essentially tau S minus right? So this is written here. This is written here, and now if I put the value of tau, it will become this. This is the famous or widely used equation for delta TB, and yeah, it depends on, you can see, it depends on cosmological parameters like Hubble parameter, baryonic density parameter, H, delta, all these things. So, if you want to model 21 centimeter signal from cosmic dawn and epoch of ionization, you have to actually calculate this delta TB, and that depends on spin temperature, CMB temperature, and also the density delta B, that is the over density that Tirth talk about, baryonic density and Hubble parameter. Now, this delta B will come from the structure formation in-body simulations, and also H Hubble parameter we know from our cosmology. Now, what you need to know is XH1, that is the neutral fraction at each location of our universe. So XH1 is a function of a spatial coordinate and as well as also Z, redshift. So you have to model this, and also you have to model spin temperature. These two things you have to model using numerical simulation, or you can also model using analytical calculations. That other people will talk about how to model XH1, TS, delta B. So once you know all these quantities, you can actually calculate delta B at different locations in the sky. And then you can do various statistical calculations like power spectrum, bispectrum. You can also interpret observed data, right? Okay, so one last calculation that I did not talk about is a tau. How to calculate tau, the H1 optical depth. How to calculate. So I'll not go into the details, but I'll show. I'll give you some very quick overview how to calculate it. So tau is, as I said, it is integration of alpha nu dl, right? So alpha nu absorption coefficient. So alpha nu can be written as this h nu e by 4 pi line profile that is also frequency dependent. So this is absorption coefficient, right? Now, what are the processes that that is actually helping to absorb 21 centimeter photon? So you have this stimulated absorption, right? You have this radiation background. So actually, you have to write N0 and then rate. So this is the number density of hydrogen atom in singlet state, and this is the rate at which it is going to the triplet state. So that is the absorption, but at the same time you have emission. So some triplet state atoms are coming down to the singlet state. So that you have to subtract, and that is N1 B10, right? So that is the net absorption, right? Now here it is. What is this? This is the this is line profile. This is called line profile. So this basically tells you the frequency response of the background photon. So you have so you have 21 centimeter photons in the background, but it is not only the 21 centimeter photon, but 21 centimeter photon plus minus. So you have this photon with frequency so 1420 megahertz. So it will be absorbed by a ground state hydrogen atom. But not only this, but plus minus delta nu. So let's say you have a 1420 plus plus something, let's say 10 megahertz plus minus, those photons will also be absorbed or emitted, but response of that is lower than this. So if I plot phi nu line profile, it will be something like this. So it basically tells you which are the photons that will be absorbed and which are not absorbed or emitted. Right now, the normalization condition is phi nu d nu is essentially 1. Right. So okay. So right. So now this is alpha, right? And now we can actually write all these quantities, like we can use all those relations like N1 by N0 is G1 by G0. Or we can write like this 1 minus E star by Ts. We can use this relation to write N1 in terms of N0 and this quantity, right? And then we also, so there is also relations of B10 by B01 in terms of, so I forgot actually. Can I take 5 minutes more? Okay, so I can take 5 minutes more. Just a minute. I forgot the relation. Yeah, so that is G0 by G1. And then A10 by right. So see, we can convert all these numbers in terms of Ts, T star, Ts, and these constants, right? And we know A10 is this. So we can also put the value of A10. So if I if I put everything together, we'll get tau as this. I'm not deriving this equation in detail, but one can always write tau as this 3c cube yeah. So one can write this equation in terms of this, and as I said, how to get here. So I have, see, if you use all these relations, you will get here. And you see, this is this depends on neutral hydrogen density total neutral hydrogen density. T star we already know, Hubble parameter, that is spin temperature, right? So you can actually calculate this tau, and if you plug that in, you will get the equation that is written below. Okay. So if you are still unsure about how to calculate that, you can talk to me after this lecture. So basically, now we have these equations, right? So now to summarize my lecture, so I explained to you why neutral hydrogen is important in probing the epoch of reionization, and what are the processes that determine the signal, particularly the spin temperature, and what the exact quantity that we can actually measure, that is the differential brightness temperature, and how it depends on the different cosmological parameters, density, and some constants. Right? So yeah, so now we can use this delta TV to study various things. Okay. So thank you. If you have any questions, you can ask.
Nu is the absorption coefficient.
Yes.
Right. Then why there is B10? It is emission.
No, so this is the net absorption. So you have this part is absorption, but what we are interested in is in the net radiation. Let's say 10 atoms are going from singlet to triplet, but at the same time some atoms are coming back to singlet state. So if it is, so we have to actually take the difference, and that will give you the net absorption, right? So let's say 5 is coming back, so your net absorption is 5. So that's why I have written this.